predominantly used in mathematics as well as physics is S, you know, the displacement, how far you've gone. In general, you know, when I think about a situation where I have some kind of a function, you know, if I have kind of a starting and ending location on the x-axis, then it corresponds to places along the curve. What I'm looking for is some way to talk about, you know, the distance along the curve between these 2 points. So I'm going to try to darken this in a little bit. You know, so exactly how long is that curve, you know, as we follow the whole shape of it. The idea that we're going to use to kind of generate the formulas for this is just to think of taking this thing and if we were to, you know, sort of chop it up into a bunch of little pieces. I'm going to use the notation that that little piece is a ds. You could write a delta s if you want. In terms of deltas, finite increments as opposed to differential distances. But the idea is to think, well, okay, you know, if I had this thing chopped up into a whole bunch of these dx, I know that, you know, s is going to be the integral of the dx length, and somehow I should maybe say context. The basic idea that we're going to build it off of is to pretend that we kind of zoom in on this, you know, this little ds segment, and we're going to think then that if I really zoomed in, what I might see there is sort of a straight segment that would be the length of ds. If you take a calculator, you know, take any function and zoom in on any part of the curve, no matter how curved it is, if you zoom in far enough, it looks like a straight line over, you know, small distance. So think of that same kind of thing, you know, zoom just as far in as you can, so that these are, you know, differential distances. And then you'd have what, you know, you could then say, well, you know, I kind of have, you know, this triangle that I could imagine, you know, being right here, you know. And what? There would be a corresponding little dx distance and a dy distance. You know, how little movement up and down, little movement side to side. And, you know, with the way that I've drawn it, obviously I'm trying to generate this sort of Pythagorean, you know, feeling for this. And so, you know, if that's a reasonable way to think about this, then, you know, this sort of generates the idea that what, that ds squared is a dx squared plus a dy squared. And we just sort of start with that as the basic notion of how arc lengths relate to the differentials in x and y. Then I can generate basically 3 integration formulas for the different kinds of situations that we face in this course. Currently, this book only gives you trouble with 2 possible situations. I'll talk about the 3 orientations. All right, so what we're looking for then is, you know, in 3 different ways this could be the settings. First, it could be much like I just drew back here, in that, you know, you see this as kind of a y equals a function, you know, x kind of form. You know, when things are described this way, if I'm going to try to get little, you know, little pieces, you know, ds long, what I'm going to imagine is, you know, is having basically a slice this way, you know, so that if this is dx, you know, I guess I drew it in a bad spot here, but, you know, I'd be looking at a little ds segment on top. So I, you know, still have that same kind of ds, you know, versus a dx, you know, down here, kind of a look to it. Okay. But what it says is, in other words, that, you know, if I'm writing the function in x and I'm kind of chopping it up in x, you know, and I'm, you know, maybe in the same kind of manner looking for an arc length from a starting point out to some, you know, ending point. And that may well be described in terms of x, you know, from A to B. Then, in other words, what would be nice is to say that, all right, well then this arc length is an integral, and it would be nice to have an expression in here that I could then integrate with respect to x, because these kinds of functions work well with chopping it up in the x direction. So it's a natural fit, in other words, to work with a dx-oriented differential term. Well, what that would mean, if I'm going to get s out of this thing, and I'm integrating with x, that would mean that the thing in here has to be ds dx. Because you can imagine that as these canceling, giving you then the integral of ds, which is certainly s. Right, so that's the sort of structure I look for when we're given this explicit y equals f of x kind of form. Similar thing, but working upward. If you have functions that do this kind of a thing, in other words, some x equaling g of y sort of a function, described kind of the opposite dependent variable as usual. Then, much like here when it was written in terms of x, it was nice to chop it in x. Well, here, if it's written in y, it's nice to chop up your integral in terms of a little dy kind of a segment, because then the y's go with the y's that the description has. But again, you can see that there is this little ds piece here, and we still have kind of ds related to the dy. And so what it says to us really is that if we want to calculate the arc length, I want to be able to integrate some expression with respect to y here. And again, because of cancellations and stuff, right, ds dy would be the appropriate thing to integrate. So we're going to look at how do we get those terms. The last, and you can see that this is just really take this picture, turn it at 45 degrees, or flip it over the y equals x, and you get a picture sort of like this. I don't know if you guys needed this thing about exploitation of students, but I guess you can sort of read it still. The last sort of context, at least for this course, that we talk about Arclangth, is when you have parametric equations, meaning that rather than describing x in terms of y or y in terms of x, you describe x in terms of t and you describe y in terms of t, and then the two of them put together, right, gives you the x, y coordinate. So you say, all right, t equals 0, calculate x, calculate y, then you know where you're starting. You put in t equals 1 and it moves you, put in t equals 2, it moves you again or whatever, right, to new x, y coordinates. So, what's the typical picture here? Well, it really depends a lot on what you have for functions, but often these are the kinds that just sort of swirl around and then whatever. There are these sorts of crazy shapes where they usually show an arrow for positive time. Think of spirographs. I don't know if you guys know what a spirograph is. Way back we shapes. I guess these days with all computers, you guys probably missed out on spirographs. Anyway, you get these crazy curves that wiggle around and around. And, just like any one of these where, I might say I want, from C, to D or something, I want to know what is this arc length in here, so you'd integrate from C to D. Over here, you're essentially going to say, I've got a time equals, say, time 1, and, maybe you want to find the arc length out to here, which is at t equals t2 or something. So you're going to want then an integral from time 1 to time 2. And again, if these are all described in time, it's nice to have a dt here then.
that says that therefore this must be ds dt in order to generate S. So they're all of the same flavor in the sense that I need to build an arc length by integrating with respect to some variable a thing that's the derivative of arc length with respect to that variable. They all have exactly that form. So basically what I need to do is say, all right, well, you know, what is the ds? I see a ds over a dx over a dy over a dt. Let's get a handle on ds first. Well, ds, if you know ds squared is that, then what? It's got to be the root of this dx squared plus dy squared. Right? And then when you ask, well, you know, what is ds dx? Well, let's just take this, right? If I need ds dx, what? ds dx would be this square root of a dx squared plus a dy squared, right? All over dx. Now, I want to get things that I can work with as, you know, I mean, this is now the dx dt. I want to substitute in here, but I got to have something that makes sense to me calculus-wise. And this with all the differentials is a little hard. So instead, you know, think about it as what a square root of a dx squared and a dy squared over a dx squared, right? Everything in the root. Right? And then just simplify it, right? Dx squared over dx squared is 1. And a dy squared over dx squared is a dy dx squared. And that's all in the root. So we're saying then under this kind of situation, this is the term that goes in here. And I would just have then an integral from a to b of the root of 1 plus dy dx quantity squared dx. That's the arc. There's the box in the book. Except that they write dy dx as f prime for beta squared.